Welcome back to the channel. In today's video, we are going to build a 12-to-1 compression 383 LS1 engine. This is part 3, I believe, in this engine's build series, and it's build day. We're going to build this entire engine from a bare block to a complete, ready-to-dyno engine. So, like always, we've got all the parts laid out. Let's go over them really quick, and then we can get to work. We're running basically a rendition of our Smeding 1300 horsepower rotating kit, except for we're doing a 4032 alloy forged piston. So it's going to run one of our 4-inch stroke crankshafts, good set of H-beam rods with ARP 2000 hardware. We're running an Icon 10-over forged aluminum piston. And then the camshaft we're going to run in this guy is decently healthy. It's 247, 255, 113 LSA with 4 degrees of advance, and 614 lift, intake, and exhaust. This physical camshaft I actually used to run in one of my 404 cubic inch combos with the same heads that this engine's getting. So it'll be cool to see the cam going back into an engine and making sound again. It's just going to be a naturally aspirated combination. So the rings are 22 on the top and about 26 on the second. We're going to try something different. We're going to run a little extra second ring gap, just a theory we want to test. And then we're running a low tension oil ring to seal up the cylinders. The crankshaft has already been balanced, as you guys saw in the previous video, as well as the block has been fully CNC machined. So today, we get to now start the fun part of putting all the parts into this awesome engine block, starting with the camshaft and then moving to the rotating assembly. So whenever we build an engine here, we always install the camshaft dry, actually. And the main reason for that is so that once the camshaft is in the bearing shell, if there's no lubricant on it, we can glide the camshaft back and forth against the bearings and feel for any tight spots. If you have this camshaft totally swallowed up with lubricant, you're not going to feel that because you're going to be forcing and pushing against the nice sticky bearing guard. But if it's dry, it just glides. And that's what we're looking for. Since it's perfect, we're just going to push it a little bit forward, and then we'll apply a little bit of bearing guard against those journals. Now, I'll rotate the camshaft and push it back into the bearing shells, kind of in this, oops, too far. But you get the idea. Now it's lubricated, and it will be held in place. Gen 3 LS thrust plates used a flange hex head bolt, whereas Gen 4 uses a countersunk design bolt. Every LS we build, we always upgrade to the Gen 4 style. The way these countersink bolts bite into the cover, it acts as like a secondary lock. Not only do they come with Loctite on the threads already, but that wedge that's created when you torque it just really locks them in place. So every LS build, we always upgrade to the Gen 4 design. And because there's already Loctite on the threads applied, we don't need to add any extra. It sounds really loud and scary. I'm barely on the trigger, and it's just that Loctite getting pushed into the block. And then we'll just torque these down to the factory spec of 18 foot-pounds. Okay, now that the camshaft is installed, we're now going to drop the crank in. In this engine, we are running a full set of standard King XP series tri-metal main and rod bearings. And on the mains, that gives us clearance of 2.4 to 2.6, and on the rods, 2.0 to 2.3. So right about 1/1000th of bearing clearance per inch of journal diameter, which is kind of the industry standard, especially for an engine like this that's going to be naturally aspirated, high street performance, not a full race engine, and not a power adder. So we'll stick to that 1 thou per inch of journal diameter, and that'll give us a good running engine for a long time. We'll come back, put a little more lubricant on, And guys, there is nothing wrong with spinning the crankshaft in the journal without torquing things down. I saw somebody in the comments lose their mind that I did just that. And I don't get it. I'm gonna keep doing it because I've always done it. It's a good way to check to make sure everything's nice and straight before you start bolting these caps down. And these caps are numbered. You'll see that there's little numbers on them, and they have to go back in order, and they have to go back in order the direction they were facing. Now, there's two ways of doing the next step. One way is to take a couple mallets and drive the caps down like that. The other way is what I do on these engines, and I just put the impact on its lightest setting and just run the bolts down lightly to bring the caps flush. I've done it like that on countless engines, and I'm going to keep doing it. Now, LS engine main bolts torque in 3 different steps, 2 really. We're going to torque all of them to 15 foot-pounds, and then we're going to torque the inners to 80 degrees and the outers to 53 degrees, and then we'll torque the side bolts to 18. The main bolts in an LS engine, even though they are torqued to angle, they are not torqued to yield, and they can be reused. The only fasteners in the LS engine that cannot be reused, that are torqued to yield, are the head bolts, the stock connecting rod bolts, and some of the camshaft bolts, depending on the generation and the engine. The main bolts can be reused. Now, this engine has already been rebuilt once before, so because of that, we are replacing them just because they've already had a bunch of torque cycles. But if this is the first engine rebuild, I would have no problem reusing the bolts again. Now, before we final torque everything, we're going to go ahead and set the thrust in the engine. We're going to align the cap to the block, and then we'll measure our crankshaft thrust end play. The way we align and set the thrust is we're going to drive the crankshaft with a mallet forward and then backwards again. And that's going to take that main cap and align it straight to the block. So I'm going to take an aluminum drift as kind of our dead hammer. Now it's going against a hardened forged steel crankshaft. This is not going to hurt this crank. Again, we do this on every engine build. We'll go rearwards, and we'll come back to the front. Before we actually measure the thrust, I'm going to go ahead and final torque down the center main cap. Okay, we have 4 thousandths, almost 5 thousandths of thrust, which is perfect for this engine's application. So now we can continue and final torque all of the crankshaft hardware and main cap hardware in and lock this guy into place. And before we go any further, we're going to go ahead and mark these bolts. That way we know and everybody knows that they have been final torqued and they are ready to run. Next, we're going to install the side fasteners for the main caps, and we're going to torque these to 1/8 foot-pounds, 18. Next, we're going to install the timing set. Now, this engine already had a Rollmaster timing set on it, which are really nice, and it showed no signs of wear, so we're going to put it right back on, and I'm just going to line it up dot to dot. And so we'll put 0, there's a 0 degree marker on the crank sprocket, and there's a corresponding 0 degree marker on one of the teeth. So on a LS and on a Chevrolet, you're not lining up the keyways, you're lining up that 0 degree marker that's on the teeth. On a small block Ford, you line up the keyways. They're each a little different if you've ever built them. And these are fasteners that I do use Loctite on. Cam gear bolts and oil pump bolts. I like to Loctite them right into place. Those are bolts you do not want to risk backing out of an engine. Now you might see the chain and it might look a little dirty, and that's because we didn't really clean it. We don't want to take all the oil that's already in the end links out of it. So we just gave it a nice wipe down, and it's going right back in the engine. And again, we're going to line up the dot on the gear to the 0 degree pointer on the crank gear with it splined on the 0 degree keyway. And I like to torque these to 25 foot-pounds. And again, they are torqued, they're Loctited, they're not coming back out in this engine build. So let's give them some blue marks. Now, I also like to go straight and do the oil pump before we put the rest of the guts in the engine. It's much easier to get the oil pump gears aligned in the housing when there's not a ton of rolling resistance in the engine to prevent you from turning it over. We are going to upgrade this engine to run the Melling 10295 performance oil pump, and we're going to install the Copo Camaro pressure spring. Ooh, ah. So, LS oil pump, actually every oil pump, but LS particular has its pressure relief valve located in this cavity underneath this plug. And all it is a spring of a predetermined stiffness that when overcome by oil pressure, the spring collapses, it gets pushed down by the excess oil pressure, and it opens a valve that lets the oil system bypass the engine so you don't overpressure the engine. Yes, too much oil pressure can actually be a bad thing. It unnecessarily heats up the oil, causes cavitation, and some other things. But with these Melling kits, they include what we call the Copo Camaro spring. And if you read this little booklet, the spring boosts your pressure 25 psi over the stock value. The stock pressure relief is set at 60 psi, and by putting the Copo spring in, we'll have a maximum allowed pressure of 85 psi, which is not too much to hurt the LS engine design. So all we're gonna do is pop this plug out, pull out the spring that's in there, shove this Copo spring in, clean the plug, put some more Loctite on, and tighten it back down. And I just use this little rod vise that we have here just to hold her steady. And it's an 8mm plug, in case you're wondering. I see a lot of people try to use a 5/16 Allen, and it just strips this guy. So make sure you get an 8mm. It does have Loctite on it from the factory, from Melling, so make sure you got a good fit on it. And boom, there's that stock red spring. We're done. You're done. New Copo Camaro spring. We'll slide that in there. And then I'm going to take this plug, I'm going to brake clean off the old Loctite, put some new Loctite on, and then we'll torque it back into place. Just a little bit. And I don't have a torque spec, I don't have a torque value, I just do this off of feel. But we'll pop that back in, get that plug threaded without cross-threading anything. And then I just give it, I don't know, kind of like a spark plug feel. Just right there. You'll feel it get tight. And that's it. This pump is now modified with the Copo spring, and we can pop it into the engine. All right, y'all want to get controversial? Let's get controversial. LS oil pump install. I myself have a video on the internet showing the correct way to align your LS oil pump. And it involves taking this cover off, it involves getting feeler gauges, it involves doing all this stuff, torquing this, doing that, tons of steps. And that is, I think, the best and the most accurate way if you had all the time in the world to just play and tinker with the motor. However, I have actually spoken one-on-one with the Melling engineers and have received their opinion and their thoughts on how they want people to install their oil pumps. And I'm going to show you guys that. Now, Don't come at me in the comments if this is not how you like to do it. Guys, there are tons of ways to build an engine. There's no right way, there's no wrong way, there's just different ways. And the way we do it is the way I'm about to show you. And this is also the way that the milling engineers who designed this pump want us to do it. So if you're mad at me, you must be mad at them. So we're gonna take the pump, we're gonna spline it onto the crankshaft, we're gonna get our bolts, they already have Loctite loaded on them, and we're gonna screw them into the block like so. I am not going to remove that front cover. Spoiler alert. We'll take a drill or an impact, and I'm just gonna run them down. It's okay if they touch off. And I'm gonna get a wrench really quick. Now, I'm gonna back these bolts off a tiny bit. So I ran them down just until they touched the pump. I'm now backing them off the slightest bit. And what we want is to be able to twist and rotate the pump just a little bit in the block. See that, guys? See how I can just barely move the pump? That's all the play there is. That's what everyone is getting all fussed about, is that itty bitty amount of play. So now what we're gonna do is we're gonna take some break-in engine oil. This in particular is the Driven BR40, and we're gonna shoot it right into the throat of that oil pump. A whole bunch of it. Don't be scared. Then we're gonna take a crank bolt, put it on the end of the crankshaft, and we're gonna run this dude in. And this is all we're going to do. We're gonna hold the block in place, and we're gonna roll this pump. We're gonna get that oil all throughout those gears. We're gonna move the gears in the housing of the pump. And this is aligning everything inside. Now, as soon as you're done with that, grab your torque wrench and torque these down to 20 foot-pounds. One, two, three, four. That pump is now installed. The gears are properly aligned in the housing. It has a Copo spring in it, and it will operate and function forever. It's that simple. Now, if you are the type of gentleman who, on every engine build, wants to take that cover off and play with feeler gauges and play with shims, that's awesome. I congratulate you. Keep doing it if that's the way you want to do it. But that's the way that we do it now, and it's worked for every single LS engine that we have ever built. Next step in the engine build is the assembly of the rods and the pistons. We've already got everything laid out. These have narrowed rod bearings, and you'll notice that the rod has a larger chamfer on one side than the other. That large chamfer is what goes against the crankshaft, and so it's very important that you put your rods and your pistons together in the correct orientation and not flipped around backwards like so. So, with everything laid out correctly, we're going to take a little bit of bearing guard, and I like to put a little bit on the first piston bore and the wrist pin of the connecting rod. So that way when we install the wrist pin, it is properly lubricated and we don't accidentally gall anything on first startup. And you really want to use a thick assembly lube for all this stuff. I don't personally like to use engine oil. I know a lot of people use engine oil for these parts. My thought process with that is if the motor sits for an extended amount of time, that engine oil is going to run down and out of the engine compared to some really thick and sticky bearing guard, which will always be in that place. So that's just my 2 cents for whatever that's worth. Now we're just going to work these clips into the pistons. These pistons have what's called a wire lock, and in the piston there's a receiver groove. And basically we're just trying to get that lock to spline into the receiver groove in order to retain the wrist pin. Just like that. When you're done, the wrist pin should be captured. Everything should have a little bit of play. The rod should glide nicely on the wrist pin. It shouldn't be tight or bound, but it shouldn't be loose. You shouldn't be able to pivot this stuff. And this assembly is ready to rock, and you're ready to go in the engine. Whenever you insert the ring into the piston, always give it a little wiggle check. Make sure there's no burrs on the gaps that are going to prevent that ring from spinning nicely in the piston and not scratching it up. So to start with, because this is a stroker engine with a shallow piston, the wrist pin hole penetrates the oil rail. And so it has this really thick, hard steel spacer ring that acts as a support to give the oil ring support in those two spots. Now, this ring does not spin and it does not touch the bore of the engine block. And to prevent it from spinning, there is a little itty bitty dimple right there that we need to align with this cutout for the wrist pin. So I just bring it around like so, and then when it gets about here, I grab it, pull it away from the piston, and then drop it into that groove. And then we'll push it all the way down, and you can see in this spot, I don't have that dimple there. And so we'll take some small needle nose pliers and just pull it a little bit. And now you guys can see how that dimple lines up with the wrist pin hole. And that dimple needs to go down so that it can't spin past it. Then you can install the oil spring and then the oil rails that actually touch the block. And your oil ring assembly is complete. Second ring in this piston kit has a little dot on it. And that dot, hold on one second. That dimple is to let you know that that goes up. So that this one goes down to prevent it from spinning, but this one is just a marker that tells us that dimple needs to be facing up for the ring to function properly. Sometimes the top rings have it as well. This particular set does not. The top ring can go either direction, so it does not matter how we install it. And we'll rinse and repeat for all 8 cylinders. One last tech tip before I finish this install. Oil rails, on the very end of them, they have this little hook that goes where the gap is. I always like to put that hook facing up on the piston instead of facing down. But my theory is if it's facing up, maybe it'll be easier to install. I don't know. No, it probably wouldn't because it doesn't even touch the block, but I don't know. It's something I do. I think it, Jacob tricks. All right, rings and rods and pistons are installed. Now, these bearings have an upper and a lower on them because they're an offset bearing design. See how the bearing is not perfectly centered in that cap? That's to give us clearance for the crankshaft radius or fillet. And the bearings will say on the back of them, now you guys probably won't be able to see this on camera, but there's an L. Yeah, I don't know if you're gonna see that. There's an L for lower, and the other side has a U for upper. The lower goes in the cap of the rod, and the upper goes in the beam of the rod. First, I just give it a wipe with a blue shop rag, shop towel. And then your fingertips are incredibly sensitive. You wouldn't really understand how sensitive your fingertip is and how fine of a scratch it can actually feel. It can detect scratches and defects under 1/1000th of an inch. If there's a scratch that's less than a thou deep, your finger can feel that. And so I like to take my thumb and I make sure it's clean, and I just like to push it against the body of the rod where the bearing sits. And see right there, I felt just a little bit of debris. And so I'll spend a little time, get it knocked out, make sure that feels nice and clean, and then I move on to the cap side. And it's just a final check. Is it scientific? No. Is it silly? Maybe, but it's a habit that I've started doing, and I've caught a bunch of stuff just feeling it with my thumb. And again, the lower bearing goes in the cap of the rod, and the upper bearing goes in the body, the beam. I like to use this as my thread lubricant on high torque fasteners. It's the cleanest stuff to work with. I really don't like working with the ARP lube anymore. It just makes such a mess. And even after the engine has ran for a long time, it leaves this sludge in the bottom of the oil pan, and I don't know. I don't like it. The CMD stuff seems to mix and blend in with the oil once everything's hot and running, but it still gives us that thread protection and lubricant on the final torque pass. So that's what we use. Okay, I've already thoroughly washed the block, but the next step in the process would be to make sure that those bores are super clean so the rings can break into nice clean metal and there's no debris or contaminants. So that's already done. So next we're going to take some break-in oil and thoroughly lubricate the walls of the cylinders. You don't need much, but you don't want to be skimpy. So go ahead and just get enough to lubricate the whole cylinder sleeve so there's no dry spots. And again, we're just using some break-in oil in this tube. All right, now it's go time. We're gonna start slamming pistons into this block. You really wanna make sure that the journals on the crank are super clean. Make sure there's no dust, no lint, no nothing. Again, I just take my fingers and just kind of give it a final wipe down. Make sure we have the right side piston here. And I am a huge fan of this style piston ring compressor. I hate the adjustable ones, and just buy the one that you need for your bore size. It makes this job so easy and simple, and you don't have any risk of really messing up the piston rings or the piston when you go to install it. And I think, I'm like 90% sure that if ARP, because ARP also makes these, if they don't have one in the catalog for your bore size, they will make one for you. I'm like 95% sure that they offer that. So there's really no excuse not to use this. And with one good swift blow, pop the piston in the block, reach around, grab the connecting rod, and glide it up to the crank journal. Make sure that the rod beam and the cap have the same number laser etched onto them. They are married and have to go back together. When you have those bolts bottomed out, you should be able to slide the rod on the journal with no resistance. If there is resistance, stop. Something's not right, take it back apart, reassess what happened. Now we'll roll the motor over. And we'll go to the next. So again, I wipe it down. You'll feel anything if there's something. Work the piston rings gently into the piston and your ring compressor. It should just glide in. You shouldn't have to force any of this if you're doing it correctly. Take your time. And there we go. I like to push it down quite a bit. That way you can locate the piston in the block, and then we'll take that compressor and push it up square against the block and then pop it with your mallet. That rod has 278 laser etched onto it, so this cap also has 278. Every single time you want to check that. And as you assemble the engine and as you keep adding rods and pistons into the block, you should notice a gradual increase in the resistance and the friction it takes to roll the engine over. It should slowly increase with each piston. If you do one and out of nowhere the block is super hard to roll over, stop. Take it apart, reassess, see what's not right. So that rod has 408 on it, coincidentally, and this cap also has the same. Give it a wiggle check, it passes. We can go to the next. Now, I have been working with this exact impact gun for years. I have tightened thousands of bolts with this impact gun, and so I am not afraid to start a bolt, especially a very important bolt like the rod bolt, with the impact. So don't at me in the comments. I don't want to hear it. Halfway there, we're now moving on to the next side. So now you guys can see it from this angle. I square the compressor up against the block, make sure the valve reliefs are straight, make sure the rod is in the right spot, and then with a swift pop, pop it in the block. Now that the short block is assembled, we're going to final torque the connecting rods. And as soon as we're done torquing, again, come back, little paint marker. That way you know, I know, Ben knows, everyone knows those bolts have been torqued. And there you go. That is how you assemble the bottom end of an LS engine. Now we're going to move on and install the cylinder heads. All right, the short block is assembled. The next step in this process is we're going to bolt down. Actually, I'm lying. We've cheated a little bit. We have already actually mocked up the short block previously to filming this video so we could measure our deck height so we could go ahead and get the correct thickness head gaskets. So we've already ordered those. These head gaskets will give us 35 thou cold quench, but because it's an aluminum block, that block's gonna grow a few thou, which should give us the magic number 40 thousandths of hot quench. Quench is the distance between the piston and the cylinder head. So we already have our head gaskets here from Cometic. They're a custom head gasket for this specific engine. Cometic's really nice because you can specify custom bore diameters and thicknesses. They have a huge catalog. They're awesome. The cylinder heads we're going to run are also, these are the first set of heads I ever put on Ricky, my old red C5. They're 243 castings. They have a CNC port job in them, done by Dan Barton at Nizer Racing Components. We're running PAC 1207X valve springs with Manley hollow stem intake valve and solid stainless exhaust valves. The lifters we're going to run are the Johnson 2116 LSR link bar design. We're not running the short travel. This engine's not going to turn the RPM that's required for a short travel lifter. And we're also not running the axle oiling design. Again, the valve springs aren't that hardcore. 1207X, they're decent. Like, don't get me wrong, that's a strong spring. It's stronger than your standard 660, but it's not like a 1209 where I would say, I'd probably like to see axle oiling. So anyways, next step is we're gonna throw the lifters into the block. I'm gonna throw my head studs in the block. We'll set the heads down together, torque everything nice and tight. We don't need to check piston to valve clearance with this camshaft. I've ran it before with this combination. It's got miles of clearance. And then we'll measure our push rod length and get those ordered. So let's throw lifters in the beast. And I like to just do a line around the body, a little bit over the wheel. I don't soak lifters overnight in oil. I think that's old school, to be honest. All of these modern hydraulic roller lifters are all pressure tested when they are assembled. So the body and the hydraulic components are already filled with that pressure assembly. And so we just put a little bit of lubricant on them and put them right in the block. Oh, another question I always get is what side does the bar of the link body, what side does the link bar go on the body? The bar always faces the intake manifold. So if you come in, that's how we do them. Now, would it work the other way? I think it would, but on Gen 4 engines, there's some casting nubs in the valley that prevent you from installing them that way. So on the Gen 3s, that's how I do them. One time, I sold a set of lifters to a gentleman, and after he got them, he called back and was like, how do I run the plastic trays with the link bar? Guys, when you have the link bar, you can throw away the plastic trays. You don't need them anymore. The link bar holds the lifters in place, and they omit that plastic factory tray design. These are much more robust. I trust them a whole lot more. I've never had a link bar fail on me. Whereas I have seen the plastic trays rotate. We've never had one fail because we don't use plastic trays. Every motor we build is link bar, but it's good insurance. So now that lifters are in, let's thread the head studs into the block. Now these have already been installed because when we honed it with dual torque plates. So you'll already see these are pretty dirty, not dirty, but they're covered in thread lubricant, again, because they've already been installed in this engine. I always like to put the head gasket on first before you start putting these studs in. If you don't, you're gonna have a hell of a time trying to get the gasket over all the studs, and you're probably gonna end up cutting your fingers. Just the way it goes. And when I honed the block, at that time, I already chased out and cleaned all the threads, and so that's why we're just going straight to assembly. Normally at this point, I would also run a chaser through everything to make sure the threads are super clean for the studs to go into, but I've already done that step. To start, I'm just gonna run these in with the impact. Again, I know the block is clean. These have already been inside of it, so I'm not scared to do that. So first we're gonna run it in with the impact, and then I'll come back with a T-handle and just manually check everybody, make sure they're all bottomed out. And I just crack it loose and retighten it, and you should feel a nice, affirmative bottoming out of the stud. It should not be mushy, it shouldn't be soft. If it's mushy or soft and you can kind of keep cranking it, then you probably have a bunch of debris in the threads causing a ton of friction. These, as soon as I crack them loose, there is no friction, and it just bottoms out nice and strong, nice and firm. That's what we're looking for. And same thing with the upper guys. Okay, there we go. Without further ado, let's pop on our heads. I want to share with you guys something that a trick that my wife actually found on Instagram and showed me. Forever, I would take the washer and I would just fat finger it and struggle to get it over the stud. And my wife was like, oh, have you seen this? Is this what you do at work? And I was like, no, I have never seen that, and I'm gonna start doing it at work. Take a flathead or a screwdriver, put the stud on the screwdriver, and then just do that. And then you can just walk it down. So Ashley, I know you don't watch the videos, but thank you. And you just go boop, spin it on. So maybe you guys are already doing that. I was not though, and so I thought I'd share that with y'all. It's way easier than trying to get your fingers in there and then the washer falls or it flips upside down and you can't get it out. This is way easier. I think it's pretty funny. Now obviously the outer ones aren't a problem, but on those inner ones, it helps. These ARP washers are serrated. The serrated end goes against, I'm sorry, say it the other way. The serrated end goes away from the nut. The serrated end goes against the base material you're torquing down. And these I take a 12-point, spline the nut on, kind of hold my finger on it, and then shoot it onto the stud and start threading to prevent it from falling down into the abyss of the engine. So even though we're running aftermarket ARP studs and not factory hardware, you still want to torque the heads down in the OEM's specification. You don't want to just start on one corner and then do them all the way across and then come back all the other way. Generally, they'll all have you start in the center and then work your way out from that point. So I start there, go bottom, I cross it, go back, and then do the final corners last. Just like so. The final spec on these head studs is 80 pounds. I'm gonna go to 50 first, and then we'll do the final step to 80 second. So guys, that impact only really torqued these down to like 15 pounds. That's why I'm not afraid to use the impacts to start with. Okay, first step is done. We'll now step up to final torque, which is 8-0 for these head studs. And you want to hit your torque in one motion. You don't want to ratchet it all the way there. So even if it's running out of room, you just got to keep going. And that's why I like to start and give myself a lot of room to hit that torque. There we go, that's much more comfortable. Okay, one head done. Final head to go. There we go. Now all we have to do is torque down the little itty bitty guys on the inside of the valley. And then we can get our push rod length. Boom. All right, fellas, time to do push rod length on the 383 LS1. In order to keep really consistent, good push rod lengths across the motor, we are going to run these billet rocker arm standoffs. The factory ones are cast all the way through. None of this is machined. And you can see some variation. So we have these nice billet ones now. And we're gonna start with our intake push rod. But before we actually measure it, we are gonna start with the exhaust side because we need to make sure the intake is on the base circle of its camshaft. So put your push rod in the exhaust, roll the engine over with your thumb on top of the push rod, putting pressure on it. We're gonna roll this over until the exhaust starts to open. When the exhaust valve starts to open, the intake valve is on its base circle. Right there, the valve is opening. Now let's stick it on the intake lifter side. Take our rocker, pop that guy down. And I am holding the rocker firmly against the stand, and I have a bunch of lash. So that means our adjustable push rod is way too short. So we're gonna open it up, stick it back in the motor. Still a little short. Let's make it a little bit longer. And this is kind of just a trial and error. You gotta be patient, you gotta go through the steps. Okay, that's still too short, but it's very close. So now we'll start slowly increasing the length. Okay, right there, I'm pushing down and I have no wiggle room. So I maybe went a little bit too far. So we'll shorten it back up just a smidgen. Okay, there we go. I can hold it down firmly against the cylinder head, and it has just the slightest bit of play. Remember, whenever you torque this nut, things are gonna compress more than you can compress them with your hands. So, let's get that knocked out now. And with this ARP stud kit, these torque to 25 foot-pounds. So we'll use our nice snap-on wrench. Click this at 25 and feel it. It is locked up completely. I can't move this at all. So that means my adjustable push rod is still just a smidge too long. So let's pull the nut off the stud, pull the push rod out and make it just a smidgen shorter. Stick it back in, make sure it's on the lifter, and rinse and repeat. And basically we're gonna keep doing this until, with the rocker arm torqued all the way down, it barely wiggles on the valve tip. Just like that. I can move the rocker side to side. It's free, there's no resistance, but I can't move it up and down. There's no lash. So now we'll take this all apart. And carefully extract that push rod without moving it. And then we're gonna measure the tip-to-tip length. We have a set of these nice 12-inch calipers. And I have a tip-to-tip overall length of 7.475 at 0 lash. And that's intake. Now, we're gonna rinse and repeat and do the exact same thing for the exhaust side. Sometimes these are different. Most of the time they're not, but sometimes they are. So we always like to check both, and it's a good way of double checking yourself. So now we're gonna stick this back on the intake side, and we're gonna roll the engine over until it starts to close, and then we'll pause, and then move it to the exhaust and do the same process again. I'm also gonna bring you guys in a little bit tighter this time on the motor. So let's drop this on the intake, firm pressure down, roll it over until it starts to close. It's opening, there's the peak, and now it's closing. Take it up, and we're gonna drop it into the exhaust side, get our rocker arm. Okay, that feels really tight. I'm gonna make this a smidge shorter. Still too long. Still too long. See, our exhausts are much shorter for some reason. There we go. All right, it's a little too loose. Let me make this a smidgen longer. Ooh, it's borderline. Really, really close now. Micro adjustments. Okay, let's try that. You want there to be a little bit of lash, because again, once you torque this down, it's all gonna compress. Okay, I can move it side to side, but up, I think it's borderline. I think it's right there. I think the push rod might be a tiny, tiny bit long. So let's just pretend to subtract a little bit off the overall length whenever we stick this in our calipers. So take the nut, take off the rocker, and without moving it, Carefully extract your adjustable push rod. Okay, so I have a length of 7.44 O at 0 lash. Now, we are running Johnson's in this engine, which all call for plus 35 thousandths, but there's a little bit of a range, there's a tolerance. So let's do some quick little math. So the exhaust, 7.44 plus 0.035. Now, this block is aluminum, so I'm actually gonna go ahead and plus another 5, because it's gonna grow a little bit. That says, ideally, Johnson would like us to run, that should be an H, I don't know why I did a T, a 7.480. And then let's do the same thing on the intake. 7.475 plus 0.035 plus 0.005. On the intake, ideally, I would like to see a 7.515. Now, those lengths might be a little difficult to get, but Johnson gives us a plus or minus 10 thousandths. We could go either way. So I am in reality going to put in this engine a off-the-shelf 7.475 on the exhaust, and on the intake, I'm gonna go 7.500. Mainly because most of these push rods actually measure a little bit longer. My personal LS7 that I just put together, the push rod says on it 7.925, but when you measure it in the calipers, same calipers, zeroed out, they measure 15 thou longer. So, we're gonna put 7.475s in the exhaust, we're gonna put 7.500s on the intakes, and that'll put us together. We'll jump on the dyno, and we'll make some steam. Okay guys, we just got the push rods from Manley. We're gonna run our 7.5s on the intake and a 7.475 on the exhaust. So now it's time to finally finish building this little 383 LS1. For this engine build, we are going to reuse the rocker arms that were already in the motor. They're the stock GM LS1 bodies, but they do have what appears to be a Brian Tooley aftermarket trunnion kit. And they all feel really good. They all spin nice and free. So they're going to go straight back on the motor. No signs of wear on the tips either. That's a big thing to look for on these, or a good thing to look for, I should say. The valve train on this 383 LS1 is now complete. Next steps are going to be sealing up the oil pan, and then we can install the intake manifold. There is the chance that this engine will see some on-track use or maybe some autocross use. So to help keep the oiling under control, we're going to run Improved Racing's windage tray on the block and their sheet metal trapdoor baffle system in the oil pan. Whenever you install anything with lots of fasteners going around it, It could be the oil pan, could be the valve cover, could be an intake manifold. You always want to get all of the bolts threaded and started first before you tighten down that first one. And then I always run 2 patterns or 2 torque cycles across the whole thing. Just because it's so big and there's so many bolts all over the place, you'd be surprised which ones loosen up after you get everything torqued down. And it's a good way of double checking yourself just in case you missed one. Okay guys, the engine is basically complete. We got the valve covers on, we got the old ignition coils on, and now we're finally going to drop down the last piece of the puzzle, which is this super trick MSD atomic LS1 intake manifold. It's gonna fit under the F-body Camaro cowl and hood, no modifications needed, and this is pretty much the best performing intake manifold for the application. So I'm gonna get this torqued down really quick, and then this engine will be 100% complete and ready to dyno test. So again, like anything with lots of bolts, you'll help yourself a lot if you just get all of them threaded first before you tighten down that first one. It just helps get everything lined up, make sure that every single bolt is engaging correctly in its threads, and you won't get to the last one and realize you gotta start all the way frickin' over. And just like that, this engine is now ready to dyno. Please subscribe to the channel because the next video we are coming out with is this engine on the dyno making some steam. So really quick, leave a comment below. How much horsepower do you think this engine is actually gonna make? Again, it's a 383 cubic inch LS1 with CNC ported 243 cylinder heads, 12:1 compression, 247, 255 cam, and then a stock MSD Air Force intake. We are going to run it on E85 as well. Thank you so much for watching. And as always, I'll see you next time.